Hi guys, Shouvik here. Welcome back to our channel. So today we will have another banger of questions. So let's get started. Yeah. So on today's question we have something like longest nice subarray. So in the questions, it has what they have given to us. They have given a nums consisting of positive integers. Positive integers. So there is a nums array is given to us, and it is told that every element should be positive. Like positive means not zero also, like greater than zero. It has, and we call a subarray nums nice if the bitwise and if the bitwise AND of every pair of elements that are in different positions in the subarray is equals to 0. So subarray, I think you guys is already aware if you are following me till from very start. Then and subarray concept is they have also, like, for easy understandable purpose, they have mentioned a subarray is nothing but a contiguous part of an array. There are two things basically. One is subarray. Subarray, if they told use subarray means you have to choose the contiguous part. But if it is a subsequence, there is another term known as subsequence. If they ask for subsequence, that means you can choose the elements by skipping some indexes. But subarray, you have to choose a contiguous portions. You can't skip any index in between them. But in both the cases, no matter it's a subarray or subsequence, the order of the element should be maintained. So there should not be, like, if a particular, let's suppose if I tell you, if I ask you to tell me a subsequence of length 2, then we have 1, 3, 8, 48, 10. So you can choose any two numbers, like you can choose 1 and you can choose 8, these two. Like let's suppose 1 and 8, if you choose, and if I have asked you for subsequence, then you can give me a length 2, then you can give me 1 and 8, but you can't give me 8 and 1. So the order should be restored. You can't reorder the elements. The order, the way they have basically persist in the original array, the same order you have to follow. But for subsequence, you can skip few elements in between them, but for subarray you have to choose the contiguous part. I think it's very straightforward, but yeah, for sake of simplicity, I just quickly give you a high level brief of that. Yeah, so now we have, on this question, we have to find a subarray, and a subarray is now they have asked for nice subarray. And what is the definitions of a nice subarray? By this question, they told that the bitwise AND of any two different positions of the element. So let's suppose you choose a subarray from index 0 to index 3. So how many elements then? Index 0, 1, 2, 3, 4 elements. So out of the 4 elements, if you can choose any two pairs of indexes, and if you do the bitwise AND, I think bitwise AND you guys should know. If you don't know, then please read it out. What is bitwise AND? What is bitwise operator? So we have few operators in bitwise AND, bitwise OR, bitwise XOR, bitwise OR and XOR. Yeah, this three majorly. And or XOR, something like this. Bitwise NOT is also there. Yeah, there are 3 or 4 operators, but most commonly is and, or, and XOR. These 3 are like very common. So now in these questions, they have asked to bitwise AND of every pair. Like if you can choose any two pairs, and if you can do a bitwise AND among them, then the resultant, the bitwise AND should be 0 after doing the bitwise AND of the any two distinct pairs of the subarray you have chosen. Right? So yeah, the question is very straightforward, I have to say. And if I can quickly write the truth table of bitwise AND. So this is something like, let me just quickly connect with space disk. So I am just giving you the truth table of these things, that is of bitwise AND, so that you guys can get the gist of that. So on bitwise AND, the things is, it's working, right? Yeah, it's working. So on bitwise AND, like 1, it's just not okay. 1 and 1. So it's bitwise AND is 1 and 0. That comes to be 0. 0 and 1. It's boiled down to 0, and 0 and 0. It's boiled down to 0. So that is the TT. TT stands for truth table. So that is the truth table of bitwise AND. Now, after doing the bitwise AND of any two pairs of the resultant subarray, it should be 0. Like if I can arbitrarily choose any two pair of the resultant subarray you are proposing me, the bitwise AND among the pairs should be 0. Now what we have to return? We have to return the length of the longest nice subarray. So we don't have to return the exact subarray altogether. They are happy if you can return the length of the longest nice subarray. they are looking for length integer. Yeah, I think you guys are able to understand. Now let's just quickly go through the test cases to get a more stronger grip. So on nums, so that is the nums is given to us and the output is 3. How they got 3? The longest nice subarray they have chosen 3840. So here you can see the contiguous part. Subarray means the contiguous part 3848, and this subarray satisfies the conditions. If you can do any two number bitwise and its result out to be 0. So 3 and 8 they boils down to 0. 3 and 48 it's boiled down to 0. 8 and 48 it's boiled down to 0. So it can be proven that no longer nice subarray can be obtained, so we return 3. So apart from that, you can't obtain a subarray of size 4 altogether. So that is the longest on this case, correct? And on this test case 4, there is no like length 2 subarray at least also possible. So here you can see like note that subarray of length 1 is always considered nice. So if there is every single element is also considered as a subarray, and every length 1 subarray they told it is by default a nice subarray. So your answer should be always the 1. That's the for sure. But more than 1, what is more than 1 the longest value you can form? So that is the ask for this particular question. Yeah, now I will definitely tell you that please take some pause and think the solutions, because we are mostly on day 15, more than day 15, like we are solving almost day 18 to 19, and if you are following us still from very first, so I think you should be capable to think of at least some brute force and mostly some optimizations part after writing the brute force altogether. So here you can see the constants is altogether too large, that is of 10 to the power 5. So you can do the childish things. So what is the childish things? You can run 2 for loop, one starting from one I loop starting from 0 to n, that is from index 0 to very last, and you can start a j loop from index I to n. So the subarray is going to be considered from I to j. So this is going to be your brute force. So I think brute force is very simple. I am just going to write the pseudocode. You can write a for loop from index I start from 0 to n, and inside that you can run another for loop starting j from I to n, and you can basically start from I plus 1, and you can start your unstemp from 1, and you can do unstemp like all the subarray, like basically bitwise you can do like this particular portions, like from I to j, what is the elements you altogether have at, like in this particular range. You can do something like what you can do to check every possible pair. So yeah, you can do what you can do also. You are considered this. I am thinking do you need another loop to basically check if it is going to satisfy all the conditions? Do we need that? You can start your j from very, what you can do. So till this point it's valid, like every pair is going to be considered as this. Now these two are 0. Now you can do like on the brute. Okay, so you can do one thing. So you can basically from your j, whatever your j, you can basically write another for loop, like a k for loop starting from j. You can move this while j not equals to I. You can move to k not equals to I, and you can move your this pointer from left, like I is moving on this direction. You are starting your j from this, and there is a pointer k. You have started your k from here, and you are moving this till I boundary, and you are basically checking if your nums of k and so that is of bitwise and basically nums of, just you are moving your pointer something like this, nums of k and whatever the elements, that is your k pointer is here, your k pointer is at this particular portions. You are starting from k equals to this. So yeah, That's right. And your nums of j, obviously you can start your this pointer from here, j minus 1. So your j pointer is here. You are considering if you can consider this particular elements to your answer altogether. So nums of k and nums of j, if that at any point of time you can take another OK variable, you can start it with OK true, and if not equals to 0, then you can do OK equals to false, and then from then and there you can do a break altogether. So that is your, and if it is valid satisfied, like if your OK is okay, like if your OK is fine, then you have a answer altogether defined here. You can maximize your answer from index I to j. So as it is a zero index based, like from index I to j it is a valid. So how many elements? It should be j minus I plus 1. So the plus 1 is the total number of elements. So if your I index is 0 and if your j index at index 2, so 0 1 2, how many? 3. So if you can do 2 minus 0, it is 0 plus 1. So the number of elements should be plus 1. The number of elements should be plus 1. So like this way you can, after that you can return your answer altogether after all the for loops executed. But again, the time complexity on this case, we are doing something of three nested for loop, that is of big O of n cube. So that is going to give you a direct TLE for sure. So yeah, I think it can be done on n square also, but yeah, that I am not going to write every brute, so that you can define, but all quadratic or cubic solutions is giving to be to land on a TLE altogether. So now I guess you guys have think something on the big O of n kind of solutions which actually needed for this particular question. So now let's start on the most optimal solution discussions, optimal solve. So on optimal solutions, what actually we can optimize. So when you have a subarray question, please fix your brain, please make your brain in the direction to think of sliding window when there is a subarray question, because subarray, that means a contiguous portions, is exactly the sliding window. On sliding window also we have a contiguous portion, and on subarray questions also that is a contiguous portion. So if a particular question on subarray, then please make your brain to think at least once on a sliding window concept. Now we have already discussed, right? We have discussed multiple times. We have solved most difficult questions of sliding window. We have two categories of sliding window. What are those? If you don't know, then please go through our sliding window playlist. I have created now. Okay, I missed to mention, I have created a playlist specific question, so where you can practice the questions that we have already solved. So these playlist specific things give you a very extra benefits before your interview. Please go through the playlist that you are feeling that I need to brush up these particular topics. You don't need to brush up all the topics in the last day of the exam. What is our situation? So we just go through the topics that we think that we need to brush up. So that's the reason I created the playlist. Please go through the playlist of the sliding window if you don't know what are the two categories of sliding window. So one is fixed size, another one is variable size. So which one is going to be useful? If you know, if you are following us, fixed size, do we are good with fixed size? When we are good with fixed size, when we know our window size is altogether going to be defined at very starting of the execution. If our window size can fluctuate at the runtime, then that is a variable size sliding window. So for our case, now let's try to fit the question of sliding window altogether, and we know we are at naked eyes not able to identify something like of fixed size, because window can be vary because they are a point of validity or invalidity. Yeah, I am coming how it is how the point of validity or invalidity is going to be coming in picture. But before of that, there is a very strong mathematics on this particular question. If you can identify, then only you are going to solve this. So why I put the truth table at very first. Now let's basically reconnect both the things. So what actually basically help me to any of pairs, when we are doing bitwise AND, they become zero. So as per the constraint, we have nums can be grow and as big as 10 raised to the power 9, and if you do a 10 raised to the power 9 can be represent as a bit of 32 bits. Every 10 to the power 9 can be represented by 32 bits. Now if I can represent a particular number in terms of 32 bits. So there are 32 places, 32 bits. Now what actually can happen? So that is a, let's suppose that is a number x, that is a number x, and let's suppose that is that is a number y. Now what actually make, we know that bitwise AND is only going to be 0 when at least one of them is 0, when at least one of them is 0, right? So let's suppose if that is a particular index, if I can write the index in terms of, so please note that from bitwise we are starting from reverse indexing. That is basically helping us for different questions. But for this you can start from forward indexing or backward indexing. Both should work fine. But yeah, like I am following the genuine practice. So this index is considered at index 0. This is as 1. This is as 2. This is as 3. And like this way we have dot of how many dot of 31. Like 0 to 31. How many? Total 32 bits. Correct? So now, if at any particular index, both the index have one set. If both the index has, this one has, let's suppose, set 1, this one has, let's suppose, set 1, then can we say if let's suppose for x and y at any particular point, if both the bits are set, can we say we are not able to after bitwise AND it is going to result out a 0. It will never do, because a particular index there are two set bits. Correct. Now let's extend this concept a little bit more. Now that is that we have proved for 2 elements. Now what else for more than 2? Because we have to play. So that is proved for two elements. Now we have what we have subarray. Subarray means 1 or greater than any. There is no boundary to. There is any boundary. So that can grow as big as big of size n. Entire array can also be considered as a subarray. So if it is a subarray, so now tell me the above concept what we just proved for 2 elements, is it applicable for subarray? If there are more than 2, can you tell me if the same logic, same things is going to be true for subarray also? I think yes. It is indeed yes. It is not think, it is indeed yes. So let's suppose I am again considering 4. Now let's suppose on this time we have total of 3 elements. You can write for 4 elements also. So let's suppose we have these 3 elements. Now if let's suppose this index is set by this particular, I am writing it x, I am writing it y, I am writing it z. Okay. Now let's suppose this particular index is set by x. Now if any of them, let's suppose y has set this index, by chance y has set this index, so can I say this particular to never going to be return me bitwise AND is 0? Never, it is never going to be, because two set bits, because both have a common set bits at a particular index. So okay, y is very kind person. He basically not set its particular bit, he make its non-set. Now let's suppose z had set its particular bit. So can I say yz to fine, xy to fine, xy can make it a 0, yz can make it to 0, but if I can choose x and z, that is never going to return a 0, because again the same things, these two set bits are at same index. So now we have proved that what we have proved for 2 is applicable for 3. Now like this way you can write your own cases and this can be proved for n elements. Now we are able to generalize our answer, that is proved for now n elements. So what is our logic then? What is actually then our logic? So if there is a range of elements, from index 0 to let's suppose from index I to index j, no, and if I can and if I already told a number can grow as per the constant as big as 10 to the power 9, which can be fit as a 32 bits integer. 32 bits you can obviously represent. So from index I to j, from index, why I am repeating this line, that is exactly the fundamental of this particular question. If you understand this, the implementation is a cakewalk. There is nothing on the implementation. The implementation is just drinking a 1 glass of water. That's it. But sometimes it is also difficult. Okay. So I to j. So we have to iterate from I to j. Now from I to j, if what is how I can say this particular index is valid? How I can say this particular subarray is valid from index I to j? How I can say this? If as per the above representation, if on the 32 bits representation of all the elements, if a particular index is set, if a particular, let's suppose 0, 1, 2, 3, if a particular index is set by any elements from I to j, then this index is never going to be set by another, elements. So from index I to j, if a particular elements set its third bit, then only one element is allowed to set a particular index bit. If two can set a particular index bit in the subarray range, then these two pairs bitwise AND is going to not giving you 0, not giving you nice subarray. So that is the fundamental of the whole question. I think it's clear to you, but if you not able to exactly grip the entire things, please reiterate the video once and please try to read the question and try to do some keyboard work, hands-on keyboards, so that you can get the gist. But yeah, if you not able to understand on the first go, please reiterate the video. So that is exactly, I am totally agree, that is obviously a little bit tricky question. Like there is maths, there is bitwise operations, you have to be very strong. There is sliding window. How many topics on this particular question? There are 3 topics, man. Sliding window, SW, bitwise operation, then maths. There are 3 concepts. That is obviously a very good questions for interview perspective. And yeah, so if you are not able to digest on the first go, please reiterate once. Cool. So now I think we are ready. So what we need, so we have a sliding window, and so from sliding window we are basically trying to define a point of invalidity, right, a point of invalidity, because we know, if you don't know, please go through the sliding window playlist. If you don't know, please go to the sliding window playlist. I am repeatedly stating, so that I have multiple times, numerous times explained what is point of invalidity, what is point of validity on the sliding window playlist on the initial videos. If you don't know, please go through the sliding window playlist. So we have, I guess we are able to define our point of invalidity altogether, right? We are able to define. So what is the point of invalidity? If in the sliding window of size I to j, what we are considering, this sliding window has, we know we can represent is a 32 bits, have two elements, two or I have to say more, like greater than equals to 2. If it has 2 or more elements whose set bits is set to 1, that we actually called as set bits, whose set bits to a particular index is 1. If 2 or more elements has set its particular bits at a particular index, at a same index, if 2 or more elements set its bits to the same index, then we can say our sliding window of size I to j is invalid. And if we know the point of invalidity, and if we able to identify there is a invalidity points, then what we have to do, we have to shrink our window. That we generally do for all the questions. Yeah, I think that is the fundamentals of the entire concept. Or now rest is how you are basically implement the things. So now jump on the implementation part. So on implementation, I have taken len of nums to an n variables that we are usually do, and then I have start a map. On other language you can say a hash map. on Java, guys, and in Python it is I have created a default dict of int, so of bits. So the point to note, these bits can grow at max of 32, not more than that, because 10 to the power 9 can be represents with 32 bits. So default dicts, so this dictionary size can grow at big of 32, not big of n. I am repeatedly stating that can grow of size 32, correct? Now what? Now we have set our pointers. I and J stands for like left and right pointer that we are discussing on the OneNote. So I start from index 0, and we have start our J pointer also 0, and the window should be from I to J. That is our window, correct? And as per the question, we have already discussed, like, note the subarray of length 1 is also considered nice. So for in our array, and it is stated that num's length should be at least once to all the cases. So that's the reason our answer should be at the very minimum case, so should be at least 1. So I have start answer with 1, and we are doing standard. We are doing what? Standards variable size sliding window template. We are following standard variable size sliding window template that we are discussing from last 3 to 4 videos of sliding window. If you don't know, please go to the playlist and please check that video. That's you have to do for variable size sliding window. So now what we are doing, we are consuming, I'm not going to explain this what actually in the template. So I am going to just explain the what is this question specific gist you have to consume. What is this specific to this particular question? What is the extra basically game you have to play to solve this question? That part I will going to explain. And other, like we basically I'm considering you are coming after seeing that video. So but yeah, like I am just quickly explaining. So we are starting our J pointer. We will iterate our J pointer to very last, that is our right pointer. We are iterating from very last. And what is the J elements? We are putting it to a LE variable. So LE stands for element, and we are basically counting. CNT stands for like what is the index number. CNT basically index number. It is like index which particular. So you remember, right? So we have do a reverse indexing of 32 bits, starting 0 from very right to left, right? So CNT stands for like indexing, and we have some invalid index. We may have some invalid index. What is the invalid index? If this particular index is set by 2 or more elements. If this particular index is set by 2 or more elements. So now when there is an elements we are consuming by our J pointer, that is our right pointer, what is the bitwise? So we have maintained a bits map. So let's just push this entire things to our bit map. How we can do so? We are basically, I think I am considering you guys know about some of the bit manipulation things, but if you don't, please I will suggest you to go to some Geeks for Geeks articles. But if you don't know, like for this particular question specific, what actually game I have played here, I will quickly explain. So I have assigned the nums of J, what is the elements, to the elements, and what I am doing, I am basically checking if the right bit, if the very last bit is set or not. How we can do so? We are doing a bitwise and of elements and 1. So that's the techniques. You can check if the very last bit is set or not. So that is very simple. I am just quickly explain on the OneNote also. So if your LE has something like 0 1 1 1 0 1, and if you want to know these particular bits, this bit is set or not, how you can do? You can do a bitwise and with this. So other all are basically 0. So if that is come, so this all are result to you 0 only. This all results to big 0 only, and this is going to be give you and 1. So if this particular bit is set, and if it is not set, so if it is 0, then this also giving you altogether 0. So your entire result is 0. So if your entire result is set to be 1, that means our last set bit is set. Our last set bit is set to the elements. So the same things I have did. I did elements with bitwise and with 1, and if this is coming to be a 1 altogether, then we can say bits of CNT. What our CNT index currently we are considering? We are considering the index 0. That is from very right we are indexing. We have increased its count. And if our bits count is more than 1, that I told, what is the point of invalidity? Greater than equals to 2. Greater than equals to 2, that is the point of invalidity, right, for our case. So bits of count, if bits of CNT is more than 1, so that is actually greater than equals to 2. Greater than 1 means greater than equals to 2. We can write it also greater than equals to 2, that we discussed on the OneNote. So you can write greater than equals to 2 also, that is same things. If that is so, we are pushing what is the invalid index altogether. We are pushing this to our invalid index list. We are pushing this to our invalid index list. I will explain how it is going to help us, how it is going to be help us. So now as we have processed our last elements all together, we are doing a right shift. We are doing that is a bitwise right shift. So there are also 2 operations, bitwise right shift, bitwise left shift. So basically I'm just quickly give you what is actually bitwise right shift. So if I'm just giving you a quick walkthrough, but if you need a details walkthrough, please make a comments. I will create a separate video. So let's you have this number, that is your LE, and when you do LE right shift by 1, it is going to result to, so that is your initial LE, that is results to these bits is altogether basically out of your picture. So 1101, so this is going to be out of picture, and after that again if you do a right shift, then this particular bits is going to be out of picture. It is something like 110, something like this. So that is the bitwise right shift operator. So the last bit is going to be turned off. So last bit so let's suppose you have this window considered this, and when you do right shift, that is your window, sorry, this is your window, and when you do again a right shift, this is your window, this is altogether your elements. So that's the way actually bitwise right shift is working. So I do a right shift, so that means we have processed the very last elements, right? We have already checked the very last elements is set or not, so we don't need to do anything more on this. So we can completely neglect this bit to our answer. How we are doing? We are basically right shift, we are basically turned off the right bit altogether. Not turned off means we are not making to 0, we are altogether out from the calculations. So that's right shift will do. And for next, our index count, so CNT is for index count, we are increasing this. So like this way, when you have consumed a particular elements by your J pointer, with this particular iterations, you are successfully put the particular elements to your bits wala map, to your bits wala default dictor map you are following on language specific. You are able to successfully enter it, and also you are also able to calculate if there is altogether invalidity happened from after consuming this index J, right. And now we all know if there is a point of invalidity occur, so let's suppose after consuming these elements this LE, index 2 and let's suppose index 4, arbitrarily I am stating index 2 and 4 has more than one elements, more than one bit set. Index 2 and index 4 in your bits map has more than one, so that can be 2 or more, so that is more than one elements have their index 2 and index 4 bit set, so your invalid index on that case store index 2 and index 4. Now we are shrinking your window, we will shrink our window until our index I to J has elements for which every bits in our bits map has, every indexes of our bits map has only single bit set at max, only single bit set. So that's the things. We are running a while loop until our invalid index is going to be 0. So how? Until we are getting some invalid index, we are keep on doing the thing. So we are running an invalid index loop altogether when its length is altogether present. So what we are doing, we are copying the elements, copying an invalid index from invalid index altogether. So that is the index where actually the example that I already told, 2 and 4. So if invalid index has 2 and 4, the 4 index has popped up. So for index 4, if bits index is altogether less than equals to 1, if it is less than equals to 1, then we can say, okay, this particular index maybe has already under consideration by the last pop. This case I will again going to iterate, but if you are not able to catch, I will again reiterate. This case you can altogether like neglect for now. So now you have popped your index. Now what you can do, you are again doing the same code. I am just copy paste the same code, you are considering your LE with num size, because on this time we are on the phase of shrinking, and on shrinking which pointer we are going to work, with our num size I pointer. So we have pushed our LE to num size, and we have initialized our CNT to 0, and while our elements still exist, we are doing again the same things, right? So if this particular bit is set, now when shrinking, what you did for expanding, just do the reverse things. When shrinking, you have increased the bits count to this particular index when you are expanding, and when you are shrinking, just count down your bits count, because you are shrinking. This bit index has set earlier when you took this particular elements. Now you are altogether remove this particular elements from your valid sliding window now. So that's the reason you altogether turned off this bit. So this bit is set. Now let's turn off this bit count by 1. Exactly these things we have done the reverse on expansion. We did the exact reverse on shrinking phase. Now your elements we are moving to right shifting, and we are increasing our counter. As simple as that. We have processed this particular num size, and after this what else? If bit index count is still greater than 1. So after removing a particular elements, so this means you have removed this, which elements, these numSci elements from your valid sliding window, from your variable size valid sliding window. If you remove this particular elements, what is the, if you remove this and steal your bit index, the index for, you have faced the invalidity. So for our case 2 and 4, so for index 4 we got the point of invalidity. If it is still greater than 1, if it is still greater than 1, so that means we need to shrink more. So we can again push this index. So we can again push this index to our invalid index by, so this line basically states the things that this index 4 is still not valid. This particular, after throwing out our particular elements from by our left pointer, by our I pointer, your invalid index, which we consider the invalid index is 4, still not corrected, man, still not corrected. So let's suppose for index 4 we have 5 elements has set this particular bit. So throwing on 1 element, we are not able to satisfy this particular index. So what we did here, we did it pop. So it's still invalid. How we check this? It's still invalid. What is the statements how we are checking invalid? These things. The same things we did. The same things, bits index is still greater than 1. We are pushing again this index. We need to reprocess it. And as we are shrinking our window, we have considered this I elements to be throwing out. So we have moved our I pointer also on the same case. Now I think we have missed this particular portion only. Right? So this is something like, if let's suppose you are turning the bits down, not only index bits, you are turning when you are throwing a particular element. So let's suppose this particular element has turned bit as index 2 and 4. So when you are throwing, you have basically turned down the bit of index 2 and 4 both. So now let's suppose 4 has set by 2 elements, one you have turned down, one you have turned down. So this elements is altogether not pushed back to your invalid index. Now you have also turned down 2 also. We consider 2 and 4. These two are point of invalid index. So you have turned down 4, and at the time of turning down 4, your 2 also turned down, because 2 is also set by the elements which is at numSci. So when you are coming again, you do invalid index of pop, and on that case, let's suppose you got 2, because we have on invalid index 2 and 4 we are considering, and we can easily check on our bit index. It's on the next go, it is altogether less than equals to 1. So we can, on that case, we can just do continue, because this particular index, which if there are more than one invalid index, and after throwing only a particular elements, there can be, after throwing any elements from by our I pointer, if there is very high possibility there are more than one, there are any number of invalid index is going to be set it, because we are basically how many indexes this particular elements is set its bits, we are turning all of them down, because we are altogether throwing this particular elements, so that is the concept. So that's the extra lines we have to write. If so, maybe 2 is going to be handled by when we are throwing this numSci altogether. So that's the reasons we are writing this extra logic. Now I think after these iterations, we don't have any invalid index altogether to be present, right? We have processed for our all invalid index, correct? So if that is so, so can I say from index I to j, this is a valid window, If that is so, can we maximize our answer to max of answer and j minus I plus 1? So that is the size of the new window that we are currently considering. And again, we are doing standard j++. On this loop, we are doing standard j++, and on this loop, we are doing standard I++. I think you guys are able to consume this particular solution, and if not, then please reiterate the video couple of more times, then I am definitely sure that you are going to get the entire gist. But yeah, I have to say that is a very more than medium level question. There are maths there on this particular question, there is bit manipulation there is sliding window there are 3 concepts we have to be mastered to solve this kind of question. So yeah, now quickly discuss the TC and SC that we are generally doing, but if you are able to understand till this point, so I think TC and SC is a cakewalk. I'm not going to explain why it is big of 2n, because 2n, I think you guys are already aware of sliding window. Every sliding window things on and general taking big O of 2n at worst case. So why 2n? I'm just quickly give you a high brief. So the j pointer is moving to all the indexes, and by this while loop, and your I pointer is going to be traversed by this while loop. Your I pointer is going to be traversed by this while loop. So every elements can be visited twice. Once by I pointer, once by j pointer. So that's the reasons we are writing 2n. And inside 2n, I think here is a factor of 32. Here is a factor of 32, and here is a factor of 32. Here is a factor of 32. So in general, I can write it. There is also a factor of 32 is going to be associated because we are doing bitwise operations inside this. So yeah, that's it. That's the time complexity. It is more specifically of big O of 32 into 2, that is of 64 into n. On very mathematical term, it is like how much? What is the constant you have? You have 64 into 10 to the power 5. So because your n can grow, add bigger 10 to the power 5. Yeah, that is the time complexity for this particular questions, the most optimal solutions that I am able to came up with. And for space perspective, are we using any extra space, guys? Are we using? Yes, we are using the bits things that is going to can grow at big as 32 size, that can be grow as big as of size 32. So yeah, we can say a size of 32 which is almost constant. You can also mention if you are pinpoint that any TC or SC, any particular portions in number in numeric, then you can say it is of constant. You can consider it is a big of 1, but yeah, like more specifically you can explicitly tell in the interview, then that is going to be a bonus point for sure. You are able to exactly know what is the space complexity. Please tell like big of 32 and then mention it is, as we are able to pinpoint the exact mathematical constant. It is kind of mathematical constants for everything. We can consider it as a big of 1, but explicitly tell this is going to be a bonus point definitely for you. So that is I have to say that is the most optimal solutions that I am able to came up with for this particular question. So if you are able to understand till these points, please do subscribe to our channel and please turn on the notifications when we are going to be live with another new video for next purpose. Cool. So let's meet tomorrow, guys, with another beautiful question. Bye, guys. Bye for today. Bye.